Now let's move on to the second part of 7.2. We have been through sine times cosine type of problems. So let's move on to the next topic, secant times tangent type example. Here it is. Tangent to the 6th power times secant to the 4th power. Here's one such example. And the next problem here, tangent to the 5th power times secant to the 7th power. Again, tangent times secant type of problems. Well, these problems are in the textbook, so let me use my notebook here and let's talk about the strategy and some examples here. Okay, what if you have integral of tangent to the mth power and secant to the nth power? The first thing I advise students to look at is whether n is even, whether secant has even part. If that fails, and then move on to the next criterion, whether tangent has odd power. What if neither? That's very difficult story. We'll have to use reduction formula, which is done by repeated use of integration by part. But that exceeds the level I'm thinking about for this course, so I'm going to concentrate upon these kind of examples. So when m is even and n is odd, then well, that's totally different stuff, and I'd rather rely upon computer algebra system or something else. When n is even, that's the most standard case. When secant has even power, this is a standard strategy. Decompose secant to the even power into secant squared to a certain kth power, even, times extra secant squared. Now, secant squared is the derivative of tangent, so if you take y substitution as y equals tangent of x, then dy will be secant squared dx, so that ln secant squared, the extra secant squared, will be absorbed by dy computation. How about the other part, secant squared to the kth power? Secant squared is 1 plus tangent squared, so this part is going to be 1 plus tangent squared to the kth power, so tangent part, and this secant square will be absorbed by this dy computation. Let's go over to an example here, and this probably is the easiest example one can think of. So here it is. We see secant has even power, second power, so this is really the easiest possible case. And what you can do is take y substitution, y as tangent, and dy will be secant squared dx, as we see over here. Consequently, the secant squared dx we see will be substituted by dy, and the tangent to the 5th power will be rewritten as y to the 5th power. So what we have an integral of a power function. Antiderivative, that's easy, 1/6 y to the 6th power, and then consequently we have 1/6 tangents to the 6th power. Here we go. And here's a shortcut method if you want to bypass the y substitution and recognize that secant squared dx is directly the derivative or differential of tangent function. We can do it like that. I prefer the shortcut, but if you're not comfortable with it, you can just use standard method. Well, this may have been a bit too simple, so okay, let me create another problem here. Okay, why not? So let's call it y prime or something, a prime or something, and let's change this into 4th power. This will make the problem a little bit harder, but not too much. So what's the fundamental difference between this problem and the previous problem here? Previous problem, I didn't really have to do any manipulation to secant part because all the secant we have will be absorbed by this dy equal to secant squared dx. Here we need a little bit further computation, and Well, let me copy and paste this thing because computation will be pretty similar. So dy will be secant squared dx. So this will be fourth power, right? So what we are gonna get here is secant squared times another secant squared x dx, and then this secant squared dx, that part will be replaced by this dy, and previous secant squared will have to be manipulated as a Pythagorean identity 1 plus tangent squared. Here we go. So tangent to the fifth power, and then 1 plus tangent squared. So all these integrand will be tangent alone, and secant squared dx, that's coming from the derivative of tangent. In other words, we can re-express, we can re-express everything, this whole thing, by d of tangent of x. So all you have to do now is to take the derivative, and break up the parentheses first, and then take the antiderivative, and with respect to tangent of x, not by x, with respect to tangent of x. What do I mean by that? Let's just continue computation. So breaking up, I'm gonna get fifth power plus seventh power, and we just apply the power rule with respect to tangents. So 1/6 tangent to the 6th power of x plus 1/8 tangent of 8th power of x, and then arbitrary constant c. And that completes the antiderivative computation, and looks like some further manipulation on this alignment is going to be necessary. Oh, never mind, I'll simply copy this part, the original problem part, and conclude like this. Okay, I thought my original problem in this Mathematica notebook was a bit too simple, so I made it a little bit more complicated. I hope that was okay. Alright, we don't need this anymore. And let's move on to a little bit tougher problem this time. I just made tangent this secant squared into secant to the 4th power to make it a little bit tougher. This time secant part is completely gone, but don't be fooled. Secant to the 0th power is actually hidden. And what does it mean? N is still an even number. 0 is multiple of 2, so it's an even number. So you can do pretty much the same thing. Y equals to tangent of x, and then you have to take the derivative of tangents generating secant squared and use substitution technique. Well, here we go. We can decompose tangent to the 4th power into tangent squared times another tangent squared. Does it look unnatural? Actually, this shouldn't be, because at this moment everybody should recognize that sine and cosine squared and cosine squared are interchangeable by Pythagorean identity. Secant squared and tangent squared are interchangeable because of a Pythagorean identity again. And then cosecant squared and the cotangent squared should be interchangeable. So decomposing this tangent to the 4th power into tangent squared and another tangent squared, but everybody should see that the second tangent squared is immediately connected to secant squared. Actually, here it is, secant squared minus 1. Now break up the parentheses. What we have, secant squared times tangent squared. This is typical type, secant has even power. Now we have tangent squared here again, but then again the same comment again. We have done this kind of things so many times by now. Everybody should recognize that tangent squared is interchangeable with secant squared. Just do that. This is secant squared minus 1, so negative tangent squared will be negative secant squared plus 1. And everything is easy from this point on. Antiderivative of tangent squared times secant squared by the same kind of substitution, and we're going to get 1/3 tangent cubed. And then antiderivative of secant squared is tangent, and the antiderivative of 1, that's just x. So we have the answer like that. A little bit tougher because we do not see secant squared explicitly. True, but recognizing the tangent squared and secant squared interchangeable is a standard technique. So this is not outrageous at all. Let's see. Let's move on to the other type, a little bit different one. This time let's look at what if tangent has odd power. In this case, we are going to take y as secant. This is how we work out. So if we have some tangent to the odd power, then this tangent part can be decomposed into, let's see, tangent squared times extra tangent, but that's not enough. The secant to the nth part should generate another extra secant. So what we have tangent times secant coming out at an extra. Now tangent squared part, the even power of tangent, that's going to be replaced by secant squared minus 1 to the kth power. So everything will be in secant. This one was already secant. This one used to be tangent squared, but now secant squared. And tangent times secant, that's going to be absorbed by the dy computation if you take y as secant of x, because derivative of secant is tangent times secant. A little bit longer, a little bit complicated, yes, but essentially the same technique is being used here. Pythagorean identity and the second power of tangent secant, those are interchangeable. Let's move on to one such problem here, I think. Problem C is a good one. Tangent to the third power times secant to the fifth power. This is odd power, so we cannot use a little bit easier case. Alright, let's settle for part B when m is odd. So we can manipulate this integral in such a way that we have tangent x times secant of x comes out as separate entity. And that part, tangent of x secant of x dx, that's going to be dy if you set y as secant of x. Here I use shortcut method, d of secant x, the same deal as y is secant of x, and this is dy. The other part, everything is on secant, so break up the parentheses like these and apply the power rule with respect to secant. And here we go, 1/7 secant to the 7th power, 1/5 secant to the 5th power. Final comment, the same deal, exactly the same kind of argument will apply for cotangent and cosecant, except for the sign. So because cotangent, cosecant examples are essentially the same as tangent and secant, I usually don't deal with it too much. The only thing you have to be careful about is sign, negative sign here and there. So I kind of de-emphasize with this gray, but if you go over the exercise sets, there are some problems about cotangent and cosecant. So you can do these kind of problems on your own. Oh, no cheating. I didn't want to show you everything at first. Try on your own, and if you are kind of stopped, and then you can open up and then look up the answer key. Of course, there are more problems in our textbook and WebAssign too. So I'm going to leave those kind of things to students. And we're going to move on to the third topic and the third segment of the video.